This is problem 15 in chapter 3. The scenario is there's a long jumper who starts at this point right here. This is the origin for my coordinate system, y vertical, x off to the right. Launches himself at an angle theta naught with respect to the horizontal, initial x velocity vx naught, initial velocity vy naught. Goes to an apex height of 1 meter. And has an initial x velocity of 9 meters per second. So what we want to solve here is the total initial velocity, the projection angle, and the horizontal range. So the first thing I want to do is to solve for the y velocity. We can use the kinematic equation in the y direction that does not use time and apply it to the apex. At the apex, the velocity is speed is 0 meters per second, so 0 meters per second squared for the left-hand term equals vy naught squared plus 2 times acceleration in the y direction minus 9.8 meters per second times 1 meter. 1 meter being the vertical displacement. Invert the equation to solve first for y naught squared, and then for y naught taking the square root and obtaining 4.43 meters per second. Now that I know vy naught, I can do two things very quickly. I can calculate v naught, in other words the magnitude of v naught vector, which is by the Pythagorean theorem is vx naught squared plus vy naught squared, 9 meters per second squared plus 4.43 meters per second squared, 10 meters per second. And I can calculate the projection angle, theta naught, which is the ratio, tan theta naught is the ratio of vy naught over vx naught. So theta naught is equal to the inverse tangent of that ratio. Inverse tangent of 4.43 divided by 9 meters per second, top and bottom cancels out, is 26.2 degrees. As stated earlier in the problem, it's quite a bit less than 45 degrees. Okay, so what's left to find is the horizontal range, which is of course the penultimate most important item in the long jump. This is the way I did it, a two-step process. First of all, I figure out what T apex is and use that to calculate the flight time, which is twice the time it takes to get to the apex because of the symmetry. Think of the motion diagrams we've done in class. And then I can take the flight time, multiply it by the initial x velocity. Since the x acceleration doesn't change, the x velocity never does, and the range is therefore the x velocity times the flight time. So step 1, figure out what the apex time is, time from launch to apex. Vy of t is equal to vy naught plus ayt. At the apex, the y velocity is 0 meters per second. Initial y velocity 4.43 meters per second minus 9.8 meters per second squared. There's my y acceleration there, and I can solve that for the t apex and conclude that the apex time is 4.43 meters per second divided by 9.8 meters per second squared, and that is 0.45 seconds. And then the flight time is twice that. 2 times 0.45 is 0.9 seconds. So this guy spends 0.9 seconds in the air, which means his range is going to be 9 meters per second times 0.9 seconds. In other words, he will land 8.1 meters in the horizontal direction from where he launched himself.